So this is now lesson 8A, third part, and I will now discuss to you the lesson on gradients. Then let's have these directional derivatives of functions of 2 and 3 variables using gradient. So let's recall the formula of directional derivative of a function in 2 and 3 variables. So we have here equation 1 for directional derivative of a function in 2 variables. So we have here directional derivative of a function in the direction of the unit vector u, where we have d sub u of f is equal to f sub x evaluated at x sub 0 y sub 0 times u1 plus f sub y evaluated at x sub 0 y sub 0 times u2, where u1 and u2 are the components of your unit vector u. Then we have here the directional derivative of a function in 3 variables. So we have here the notation d sub u of f is equal to f sub x evaluated at x sub 0 y sub 0 z sub 0 times u1 plus f sub y evaluated at x sub 0 y sub 0 z sub 0 times u2 plus f sub z evaluated at x sub 0 y sub 0 z sub 0 times u3, where u1, u2, and u3 are the components of the unit vector u. Then let's recall also the formula of gradient of a function. So we defined last time as for gradient of function of 2 variables. So we have here equation 3. So del f is equal to f sub x evaluated at xyi plus f sub y evaluated at xyj. Then we have here the gradient of a function of 3 variables. So we have here equation 4. So this is read as del f of xyz is equal to f sub x evaluated at xyz times I plus f sub y evaluated at xyz times j plus f sub z evaluated at xyz times k. Formulas 1 and 2 here, which is referred to as the directional derivative of a function formula, can be expressed as a dot product, where we can now express this as the first formula is involving function of 2 variables. So we have the directional derivative of f as a dot product. So we have here now f sub quantity f sub x rather evaluated at x sub 0 y sub 0 I plus fy evaluated at x sub 0 y sub 0 j, that the components of your unit vector. So we have here u sub 1i plus u sub 2j. Then the directional derivative of the function of 3 variables. So in the unit vector, in the direction of unit vector, denoted as d sub uf of x sub 0 y sub 0 z sub 0 equals the quantity f sub x evaluated at x sub 0 y sub 0 I plus f sub y evaluated at x sub 0 y sub 0 z sub 0 times j plus f sub z evaluated at x sub 0 y sub 0 z sub 0, that product with the unit vector whose components we have as u1i plus u2j plus u3k in ijk rotation. So with that, these two formulas now can be expressed as a gradient. So because we have here the component of your formula, this is expressed as del f, that is equation 3. Then that product with this unit vector u. So having this as the components of your unit vector. So similarly, the third equation with this term here or factor, so it can be expressed as a gradient or del f, then that product with the unit vector. So these are the components of your unit vector. So we can also read this as the directional derivative of the given function f in the direction of unit vector is equal to del f dot unit vector u. So this involves two variables and three variables. So the formula that we have encountered can be interpreted to mean that the slope of the surface z equals f of xy at the point x sub 0, y sub 0 in the direction of u is a dot product of the gradient with u. So similarly, this also applies to function of three variables. So as you can see from this graph, so we have here the surface defined by z equals f of xy. Then you have here now the slope, which is tangent to the given curve.